All right, so let's do some problems. Okay. What is the capacitance of a large Van de Graaff generator? So that's those spheres. That's the name that was escaping me. Given that it stores 8 millicoulombs of charge, is that a large charge? It actually is a large charge. Um, so this is about 1,000th the charge of a thundercloud, and you're storing it on a sphere like that at a voltage of 12 megavolts. Yeah. So the capacitance is given by the charge per unit volt. Okay. 8 millicoulombs and 12 megavolts. So 0.67 into 10 to the minus 9 farads. If the capacitance per unit length of a cylindrical capacitance is 20 picofarad per meter, what is the ratio of the radii of the two cylinders? I guess. These are the this is the radius of the outer cylinder, radius of the inner cylinder. L is the length, and K is the Coulomb's constant. Let me just make sure of the formula. Yeah. Okay. And they tell you the capacitance per unit length. So capacitance divided by L is that. And this is equal to 20 into 10 to the minus 12 farads per meter. So log B over A equal to 1 over 2 KE. K is 9 times 10 to the 9. So what you have is 10 to the minus 3, that comes to the top. So, and that's 18 times 2 is 36, 1,000 divided by 30, 360. So B over A equal to e to the power of 2.78. So the radius of the outer cylinder is 16 times that of the inner cylinder. An empty parallel plate capacitor has a capacitance of 20 microfarads. How much charge must leak off its plate before the voltage across them is reduced by 100 volts? Okay, so C is Q1 over V1 should equal Q2 V1 minus 100 volts. Okay, so maybe, all right, let's do it this way. C is Q over V. Yeah. C. Okay. So you reduce the charge by that much and the voltage reduces by that much. Okay. So delta Q is C delta V. 20 microfarads. And the change in voltage is 100 volts. So 2 into 10 to the minus 3 coulombs. 2 millicoulombs. So 2 millicoulombs need to leak out. In this problem, so you want to find the net capacitance of this combination. So you want to reduce this to a single capacitor. All right, so what is it that you do? Any series and parallel combination, you do those. So this is a parallel combination, you'll reduce this to a single one. This is a series combination, you'll reduce that to a single capacitance. All right, the series combination is 1 over C equal to 1 over 5, and we're doing everything in microfarads, is the units. Okay. So this combination, that is C, that's given by this. And this is equal to 5 times 3.5 over 3.5 plus 5. So C is 5 into 3.5 divided by 8.5. Two 0.06 microfarad. So now this reduces to 2.06, and this was 8, and this is, oops, 1.5, and the combination of this is 15.75. Okay, so we've reduced it to that. Okay, now what is the next step? This is in series, so we'll combine these two. So 1 over C is 1 over 1.5 plus 1 over 15.75. So C is 15.75 times 1.5 divided by the sum of the two, 16, 17.25. Okay. So now our circuit has reduced to 2.06, 8, and 1.37. Okay, now it's just a matter of adding them. So 10.06, 11.43. So this bank of capacitors is equal to a single 11.43 microfarad capacitor. Okay. A 2 microfarad capacitor and a 4 microfarad capacitor are connected in series across a 1 kilovolt potential. So when you connect them in series, the capacitors are the charged capacitors are then disconnected from the source and connected to each other. So you charge them, and when you connect them in series, what is the charge? The charge are equal. Okay. And how do we find the charge on them? What you do is you reduce this to a single capacitance. So think of this as a single capacitance. Whatever the charge is on that single capacitance is the charge on these guys. Okay. So let's find the effective capacitance. And this is 3/4. So C is 4/3. 1.33 microfarads. Notice the effective capacitance will always be smaller than the smallest capacitance, okay, when you're in series. So our circuit is, 1000 volts and 1.33 microfarad capacitor. Charge is C times V, 1.33 into 10 minus 6 farads times 10 to the 3 volts. 1.33 into 10 minus 3 coulombs. All right, so in each of them, the charge is 1.33 microcoulombs. Now what you're going to do is, you're going to disconnect them, okay, and connect it to each terminal of like sign together. So this was positive charge, this was positive charge. You're going to connect the two positive together and two negative together. Now what will happen? Now they're parallel. What will happen is charges will redistribute. So electrons will redistribute. Why will they redistribute?
Because they want to form an electric field of zero.
They'll redistribute till the voltages across them are the same. So when they're in series, if they were equal, then the voltages would be the same. Okay. Right now the voltages on these things are not the same. The charges are the same. The voltage add up to this 1000 volts. Okay. All right. So Now they redistribute, and let's say Q1 is the charge on this one, and this is 2 microfarads, and this is 4 microfarads, and Q2 is the charge. Okay. So Q1 over C1 should equal Q2 over C2. We know C1 and C2, okay? And Q1 plus Q2 should equal what? What's the sum of the charges on the capacitor? See, the charge was not destroyed. Each one of them had Q, so Q1 plus Q2 should be equal to 2Q.
So 2.6 times 10 to the minus 3.
Very good, very good. Okay? So there are the 2 equations and 2 unknowns. Okay? All right. So Q1 is C1 over C2 Q2, which is 2 over 4 Q2. So Q1 is 1/2 of Q2. Okay. So initially they were equal, and and a third of the charge from one of them, from the 2 microfarad capacitor, goes over to the other capacitor. Okay. All right, so let me walk you guys through this problem again. When you connected them in series, the charges were equal. And so in fact, we'll do the following. C is, voltages Q over C. So on this guy, the voltage was twice the voltage on this. The charges were the same. So this guy had 666 volts, and this guy had 333 volts. So that's how they charged. Okay. The charges were equal, 666 volts, 333 volts. You disconnected them, reconnected them, and now the voltages across them are the same. Okay. So the charges redistributes such that the voltages are the same. Okay. A capacitor has a charge of 2.5 microcoulomb when connected to a 6-volt battery. How much energy is stored in this capacitor? So energy is 1/2 CV squared, or it's also equal to 1/2 Q times B. So 7.5 into 10 minus 6 joules. By the way, so a pacemaker, do you know what a pacemaker is? What is a pacemaker?
It's something that helps regulate a person's heart.
Yeah, so if this is the person's heart, you have your own electrical system that starts the sequence of firing, and if it doesn't do it on a regular basis, this is a pacemaker circuit. You charge a capacitor, and 60 times a minute this discharges through that thing. So the circuit automatically, this will charge, this will open, discharge through the heart, make the heart beat. It'll open, recharge. So that's what that is. Yeah. And nowadays pacemakers, so in the old days the pacemakers would discharge, let's say 70 times a minute or whatever. Yeah. Now what if you wanted to go for a run? Your heart's got to beat faster. So this resistance would change. Okay, so you go for a run and you got to be smart enough to figure out how to change the resistance. So it'll charge faster and then discharge.
How many uses did you say capacitors get? Like a million? Or
I'm sorry?
how many times could a capacitor discharge for SPR?
Oh.
Is it like a million? Or
Yeah, those super capacitors.
I'm just trying to think, because if you're doing 7 or 60 discharges a minute.
Yeah, well, these capacitors probably can be charged more than that. Yep. Suppose you have a 9-volt battery, a 2 microfarad capacitor, and a 7 microfarad capacitor. Find the charge and energy stored if the capacitors are connected to the battery in series. Do the same for parallel combination. So you'll see in a second that, okay, well, here's the simple formula. Energy stored is CV square. You connect them in series, the capacitance is smaller. You connect them in parallel, the capacitance is larger. So when you connect them in parallel, you store more energy. Okay? So if that's your goal, you connect all the capacitors in parallel. All right. Find the charge and energy stored if the capacitors are connected in series. So I'm just going to calculate the energy stored, okay? Series combination, 2 microfarads and 7.4 microfarads. So the effective capacitance is so C is 2 into 7.4 divided by 9.4. So the energy stored is 1/2, 1.57 microfarad times 9 volts squared. Farad times volt square is joules, and we'll keep the micro there. So in the series combination, you're storing 60 microjoules. And in the parallel combination, use 1/2. C is just the sum of the two, 9.2 microfarads, 9 volts squared. So you see 6 times the energy. So you guys know what regenerative braking is? What is it?
Say that again, I'm sorry?
Regenerative braking.
If you're braking,
Mm.
use the energy from the brakes to charge the battery.
Yep. So I was trying to remember, I think you can harness about 50% of the energy. So if you have a bit of money and you can buy a sports car, those guys the expensive sports car will use a super capacitor and they'll charge that. And when the light turns green, you can use that super capacitor to take off. Um, So parallel plate capacitor has charge of magnitude 9 microcoulomb on each plate and a capacitance of 3 microfarads when there is air between the plates. The plates are separated by 2 millimeters. With the charge on the plate kept constant, a dielectric with dielectric constant 5 is inserted between the plates, completely filling the volume between the plates. What is the potential difference between the plates of the capacitor before and after the dielectric has been inserted? What is the electric field at the point midway between the plates before and after the... All right, so here's this, and here's with the dielectric present. Okay. Has a charge of magnitude 9 microcoulombs. The charge is the same. And the capacitance is 3 when there is air between. With the dielectric constant of 5, the capacitance becomes kappa C naught. So 5 times 3 microfarads, 15 microfarads. Okay. Okay, now what is the potential difference between the plates before and after the dielectric? So V is Q over C. So V naught with air filled, Q is 9 microcoulomb and C is 3 microfarads. The micro cancel, this is volts, so this is 3 volts. And V 9, so this is C naught. C is 15 microfarad. And that's 3/5. So the voltage has reduced to 0.6 volts. Okay. That's because, see, the voltage was E times D. Remember, the voltage was E times D. And with the dielectric present, E decreased. D is the same. So E decreased, so the voltage decreased. And that's what we're going to calculate. What is the electric field between the plates before and after? So V naught is E naught D. E naught is V naught by D, 2 millimeters. So V naught was 3 volts divided by 2, 10 to the minus 3 meters. So 1.5 into 10 to the 3 volts per meter.
Would the half the distance be 1 millimeter, because you're separated by 2?
What is the electric field at the point midway between the plates? The electric field is the same everywhere. They're just saying midway just to make sure that you're inside the dielectric.
Okay.
That's all they're trying to do. E with the dielectric present is V over D, which is 0.6 volt over. So the electric field reduces by the factor of the dielectric constant. Dielectric constant was 5. This divided by 5 is 300 volt. Yep. So a dielectric, what does this material do? It increases the capacitance. Okay. So here's a mix of dielectrics, 2 different kind of dielectrics you're filling in this with. And I want you to find the effective dielectric constant, essentially. So the trick to solving this problem is, notice that this can be thought of as one capacitor and this is another capacitor, and they're connected in parallel. Okay. So let's call this C1, C2. The effective capacitance is C1 plus C2. Okay. So kappa 1 times epsilon naught A by 2, that's the area of the plate, divided by D, plus kappa 2 epsilon naught A by 2 divided by D. So C is epsilon naught A by D, kappa 1 by 2 plus kappa 2 by 2. So 1/2 kappa 1 plus kappa 2 epsilon naught A by D. This is the capacitance of an air-filled capacitance, and this is the effective dielectric constant. Okay? So it's proportional to the volume, half the volume. So in fact, you could break it up into many little pieces, have all kinds of dielectric constant. You just add the volume of those things. Okay. All right, that finishes the problem. All right, I